Swayam Prabha. Digital India. Educated India.
Good morning, students. So today we will start a new chapter, and in fact a new algorithmic paradigm called dynamic programming. Now recall that in one of the previous set of lectures you have got introduced to the idea of divide and conquer. Now examples could be like, let us take say merge sort. Now in this sort of problems like merge sort, what you do is you divide the problem and then you independently solve the subparts. So no matter whatever are the entries of the left subpart and the right subpart, each subpart has to be sorted, and you cannot bypass sorting any one of the subparts. Like if you do not sort any one of the subparts, then you are not going to get the desired sorted order, final sorted order. So therefore here there is a need that both the subparts, and in fact all the subparts that you divide the array into, needs to be independently sorted. Okay, and they do not, the sorting of each of the subparts do not depend on the sorting or the sorting outcomes of the other subparts. So typically these kind of problems, the divide and conquer type of problems, are actually solved in a top-down approach. That is, you break the problem into two parts and then you solve the individual parts independently, and you keep on doing this. Now recall the Fibonacci example that I gave you in one of the very first set of lectures. So there, if you apply the Fibonacci number computation for this problem, if you now try to apply this divide and conquer approach, we have seen that the recursion tree actually has many nodes where the same item is recomputed. This is because that the sub-problems that you divide the main problem into are not independent of each other. So this is a situation, the Fibonacci series computation is a problem where the subparts, the individual subparts, are not independent. By this I mean that the subparts can be reused to construct the larger parts. Fine. So the crux here is to store the results in anticipation that they might be reused. Okay. So this is the basic difference between the divide and conquer type of algorithms and this paradigm of solving problems, which is also termed as dynamic programming. So as you can immediately realize that here you have smaller solutions which you keep on combining continuously to get a larger solution, and you keep on doing this until and unless you have solved the entire problem. Okay, so this type of algorithms unlike divide and conquer, are are examples of bottom up approach. Okay, so unlike the divide and conquer technique, which actually tries to look at the problem from a top down perspective, the dynamic programming approach tries to look at the problem from a bottom up perspective. Now you have to be very careful while you are solving a problem. You have to, and the crux of understanding whether you need a whether divide and conquer technique or the dynamic programming technique is going to be more efficient for your problem statement, is to see that if the subparts are useful and need to be stored in order to generate the results for the larger parts, and that which means that the subparts are not cannot be independently computed. So the term dynamic programming actually, this is borrowed from control theory, which is a very fundamental subject in the electrical engineering department. Okay, so here what it means, the sense in which the term programming is used is about using an array or a table traditionally to store the results and reuse it later. Okay. So there are actually two important steps that go under that one has to take in order to develop a dynamic programming algorithm. So the two steps are: establish a recursive property that gives the solution to an instance of the problem. Solve an instance of the problem in a bottom-up fashion by solving the smaller instances first. So these are the two basic steps that any dynamic programming technique would always involve. So now, for a dynamic programming technique, there is a specific term which we need to actually acquaint ourselves with. and this is what is also known as optimization. So in any dynamic programming problem, you try to do some sort of an optimization. Okay. So what do we mean by optimization? Okay. So for an optimization problem, there can be more than one candidate solution for an instance. And further, each candidate solution is associated with a value. So you can have more than one candidate solution. That is the first thing. And the second thing is that each candidate solution is associated with a value. Okay. Now the solution to the problem instance is a candidate solution with optimal value. Okay, out of the many candidate solutions, we call the solution for the problem instance to be the candidate solution which has the optimal value. Now, depending on the problem statement, this could be this value, this optimal value could be either the minimum or the maximum value. Okay, so the optimum value could be either the minimum or the maximum value. Okay, so then there are a few terms that we have learned, that an optimization problem, first of all, is a problem which can have more than one candidate solution. Now each candidate solution has a value associated with it. Now the solution to the problem is that candidate solution which has an optimal value, and the optimal value is either the minimum or the maximum value depending on the problem in question. So the second concept is the principle of optimality. What does it say? This is said to apply this principle is said to apply in a problem if an optimal solution to an instance of a problem always contains optimal solutions to all the sub-problems of that problem. Okay. In other words, the problem is said to have optimal substructures. So if you have an optimal solution for the overall problem or for the full problem instance, then the sub instances of the problem will also have optimal solution, are also guaranteed to have an optimal solution. So it is in this way that these small optimal solutions of the sub problems or the substructures that are combined step by step in order to get the optimal solution for the overall problem instance. So this is the basic idea of dynamic programming. So any dynamic programming, this is one of the ways to identify whether your problem belongs to the class of dynamic programming or not. So any dynamic programming problem will typically have optimal substructured nature. Okay. We will start with a graph example. So since we have been doing a lot of uh, graphs and trees for quite some time, we will continue that and we will see how a very important problem in graphs can be solved using a simple dynamic programming approach. Okay. So consider the following problem. So suppose you are an air traveler. Okay. And you want to determine the shortest way to fly from one city to another whenever there is no direct flight from the source to the destination city, and you are bound to hop. So basically in this particular problem scenario, what you want to identify is, like what is the minimum number of hops you can take. So this minimum again has various different definitions or connotations. So you want to identify what is the minimum number of steps that one needs to take, or minimum number of hops that one need to uh, hop on before the destination is reached. Now this minimum, as I said, could be in terms of distance. Okay, so you might be interested in covering the minimum distance possible, or this could be in terms of flight cost. Maybe you are willing to, pay a little bit less, but then travel a little bit more. Okay, I mean travel a little for a little bit more time. So both these problem instances can be, you know, framed as a weighted graph, as we have discussed earlier, where the edges are directed, first of all, showing the flight connectivity or the flight route, and each edge has a weight in it. The weight would indicate the, it could be the time to travel, it could be the distance, it could be also the uh, price that you have to pay with that travel. Okay, so let us take a small example. So let's say these are V1, V2, V3, V4, V5 are your different cities, and the edges indicate flight routes. And for this particular problem, without any loss of generality, the edge weights indicates distance. Okay, the distance that you have to travel. So this edge weight, let us say, indicates distance. So ideally, what do you want? You want to travel the minimum distance starting from the source to arrive to the destination. You want to travel the minimum distance. This basically actually boils down to computing the shortest path from the source city to the destination city. So given the source and the destination city, you want to find out the shortest path between them, or the shortest flight route between the two cities. Okay, that is the problem statement. Now, if we take this particular example, and let's say, here we are interested only in simple paths. Okay, so let's say our source is V1 and we want to reach V3. Okay, this is our destination. So this is our source, this is our destination. Okay, now then the simple paths between V1 to V3, as you can see, are V1, V2, V3, V1, V4, V3, and V1, V2, V4, V3. Okay. Now for each of this, you can also compute the length or the distance to be traveled. So length of V1, V2, V3 is 1 plus 3, that is 4. In this case, length of V1, V4, V3 1 plus 2, that is 3. And this one V1, V2, V4, V3, that is 1 plus 2 plus 2, that is 5. So you can have 3, as I said, this is an optimization problem and you can have multiple candidate solutions. Okay. Now one of these solution which has, so each candidate solution has a value associated with it. These are the values, candidate solution, candidate solutions, and among this, here depending on the problem, since this is, we want to cover the shortest distance, so the optimal value in this case is the minimum value, which is 3, and therefore the corresponding shortest path that we want to choose in this case from V1 to V3 is V1, V4, V3. Okay, so this is how you try to formulate a problem and uh, a realistic example of candidate solutions, values, and optimal values. Now, how do we go about solving this problem? Okay. So, what could be a very naive approach? So, if we think a little bit, so a very naive approach would be to, for each vertex, you compute the length of all paths from that vertex to each other vertex and then compute the minimum of this. However, this is a extremely bad algorithm. Why? Extremely inefficient algorithm. Let's not call it bad, let's be more technical. So it's an extremely inefficient algorithm. Why? Because it's in the, so if you try to look at it, it is worse than exponential in complexity. The reasoning is very simple. So let us say that you have a graph G where there is an edge from every vertex to every other vertex. Okay. Now, if this is the situation, then a subset of all the paths from one vertex to another vertex, okay, is a set of all those vertices, sorry, all those paths that start at the first vertex okay, end at the other vertex and pass through all the other vertices. So if you try to imagine carefully and consider a graph that has an edge from every vertex to every other vertex. Okay, so a subset of all the paths, say from one vertex to another vertex is a set of all those paths. This would include all those paths that start at some first vertex and end at some other vertex and pass through all the other vertices, all the other intermediate vertices. Okay, so that means the second vertex on such a path will have n minus 2, okay, choices. Third vertex, there can be n minus 3 choices, and so on until you continue, and the second last vertex will end up having only one choice. So this leads you to a total number of how many choices? N minus 2 into n minus 3, so on and so forth, up to 1, which is n minus 2 factorial, which is worse than exponential. So now the challenge is whether we can use dynamic programming in order to build an efficient algorithm. So how do we do that? So we will solve the problem in two steps. In the first step, we would compute the length of the shortest path. And in the second step, we will print the shortest path. So here we will use the standard adjacency matrix Wij, where this is equal to weight of the edge if there is an edge from Vi to Vj, is infinite if there is no edge from Vi to Vj, and is 0 if I is equal to j. So this is the standard adjacency matrix definition. Now, if we redraw the graph that we had drawn just now, so for this, we can easily draw the W matrix. It's very simple. So this is my W matrix, and my objective is to derive another matrix D which gives me the shortest distance between every pair of vertices. So you can, as you will see, for this small graph very easily hand calculate and fill in the matrix. Okay. However, the challenge is to obtain such a matrix for large graph using some algorithmic technique. So let's call this matrix, the shortest distance matrix, as D. Now, the way you read it is as follows. D 5 is equal to 7, which is, referring to that the shortest distance from D3 to D5 is of length 7, and this can be easily verified using the left hand graph. Okay, so in the left hand graph, if you see, the shortest distance from V3 to V5 will be having a length of 7. Okay, this and this via V4. Now, how do we attempt to solve this? Okay, so we try to accomplish this by creating a sequence of n plus 1 arrays. Okay, each of them denoted as D superscript k. Okay, where k lies between 0 and n, such that dk ij is equal to the length of a shortest path from Vi to Vj using only vertices in the set V1, V2 up until Vk as intermediate vertices. So you consider that dkij is the length of the shortest path from the node Vi to Vj, but this shortest path has only nodes from V1 to Vk as intermediate nodes. Okay, there cannot be any other node other than V1 to Vk as intermediate nodes. So using the same graph, we can enumerate the sum of the dk's. So let us say d0 to 5 is length of V2 V5. This is infinity since there is no edge. Now d1 to 5. Okay, so that is, you want to find out a shortest path from 2 to 5 via the vertex. The intermediate vertex can be only V1. So this is minimum of length V2, V5 and length V2, V1, V5. This is minimum of infinity and 14, that is 14. Similarly, you keep on computing D2 to 5. Now you have 3 vertices V0, V1, V2, okay, 3 vertices. So V0 in this case is basically indicating the direct connection. So this D0 is indicating the direct connection. So now D2 to 5, so D1 is like you have only one intermediate vertex, that is V1. Here you have 2 intermediate vertices, V1 and V2. This is how you read it. So now this is D2 to 5, you see, is exactly equal to D1 to 5. Why? Because for this graph, okay, the shortest path starting at V2 cannot pass through V2. So therefore, including the V2 does not help. Similarly, you can compute D3. This is again equal to D2 to 5. Since introduction of V3 does not yield any new path from V2 to V5. So you can keep on doing this for D4 to 5. Okay. Now you have some choices. This would be minimum of length V2, V1, V5, length V2, V4, V5, length V2, V1, V4, V5, and length V2, V3, V4, V5. That is minimum of 14, 5, 13 and 10, which is 5. Okay. Then you go for D5 to 5. Again, as you see, this is equal to D4 to 5, as by including V5, you cannot have any shortest path that ends on V5 and also passes through V5. Okay. So thus we have at last computed D5 0.25, okay, which is nothing but the shortest path from V2 to V5. Okay. So in general, since dn ij, that is when k has become n, okay, is the length of the shortest path from Vi to Vj, okay, so dn Iaj is the length of the shortest path from Vi to Vj, since it is allowed to pass through all the other vertices. So I think by now you have very well understood that our D0 is nothing but W, that is the adjacency matrix, and Dn is the final shortest path distance matrix. Okay. So in this case, the dynamic programming, which I am writing in short as DP, has two important steps. Okay. First, you have to establish a recursive property with which we can compute dk from dk minus 1. Okay. The second is solve an instance of the problem bottom up, okay, by repeating the process in step 1 for k equals 1 to n. So this creates a sequence D0, D1, D2 up until Dn, where D0 is W and Dn is D. You start with D0 and you end in D. Now, if you look carefully, in order to accomplish step 1, we have to consider two cases. So, case 1 is at least one shortest path from Vi to Vj using only vertices in V1, V2 up until Vk as intermediate vertices does not use Vk. Okay, so that means in this case, since you are not using Vk in the set of intermediate vertices to construct the shortest path, so you can very well say that dkij is nothing but dk minus 1 ij, because you have not used Vk in your shortest path construction. So as an example, in the graph that we are using now as the use case, D513 is equal to D413, which is equal to 3, since if we include V5, I told you earlier also for some other examples, if we include V5, the shortest path from V1 to V3 still is V1, V4, V3, right? So nothing gets added extra if you include V5 as one of the intermediate vertices. So this case is an easy case where dkij is equal to dk minus 1 ij. Now the case 2 is a little bit more tricky.